Hello, everyone. My apologies that I cannot teach in person or at the regular time today, mainly because my baby is having a health issue. So we had to go to the urgent care this morning. But the things are getting much better. And so I'll see you on Wednesday at the same time, okay, at the normal time. So in this class, we're going to talk about the materials and energy balance. So last class, at the end, we briefly mentioned something about this materials and energy balance, right? Because we use this quite a lot, or use this concept quite a lot in a lot of the environmental engineering devices, okay? And also I think basically this section is actually the most important section of the entire 2601, because no matter what environmental engineering device we're trying to design, and they always have to follow the materials or energy balance, okay? So first, let's do a recap of our last class. So last class, we finished all the basic chemical concepts, right? So we talked about the alkalinity, which is acid neutralizing capability, right? And we mentioned about how we can calculate that and how we can convert our calculate mole per liter or molarity into milligrams per liter of the calcium carbonate, right? So this is kind of shifting it into an equivalent concentration. What we know is that we just need to multiply the millimole per liter by 50 to get milligram per liter as calcium carbonate. Right, so we mentioned how we can do this or why that is the case. So we also talked about the chemical kinetics, because we mentioned the chemical equilibrium just dictates the final state, but it never tells how fast it's going to reach to that final state. So that's related to the chemical kinetics, and we can categorize the reactions into several types, right? Into different orders. We have the zeroth order, the first order, and the second order. Right? And furthermore, there can be higher order of reactions. But we also mentioned that the first order reaction is actually the most important one. So in this class, or in this section of the materials and energy balance, we're going to further show why this reaction is more important, right? So we also talked about the reaction rate constant, which is that K in there, right? So the general trend is that the higher the temperature, the higher the K. So that's why we come up with a equation, which is K2 equal to K1 theta T2 minus T1, right? So what that means is if we know the reaction rate constant at a certain temperature, let's say 25 Celsius, okay? If we know the K1 and T1, then any reaction constant at any temperature, we can just plug in this equation. Or what that means is plugging all the parameters together with the theta value. So we know that theta is 1.0 something, right? And then plug in the temperature that we're interested in, and then we can get this K2 here. Okay, so this is basically a relationship of the reaction rate constant on the or with the temperature. All right. So in this class, we're going to learn a new topic. So this is a quiz problem that I originally designed for the synchronous class. So the first order reaction means, so there are three options. Okay, so I think we also had this quiz question in our last class. So the first order reaction just means that the reaction rate is proportional to the concentration. So what that means is R is equal to Kc, or some people may also write it as minus Kc because the reaction is consuming the reactant, right? Actually last class we also briefly mentioned about this materials and energy balance. So first is about the materials. So we gave an example of buying potatoes, right? So we have certain amount of input, right? So that's the amount of the materials that bring into the household. So we also have the consumption, which is consuming these potatoes, right? So if we cannot consume all of them, some of them will get accumulated in the fridge or in the basement, right? And if some of them have gone bad, then they will become solid waste. So this is a very simple example of the materials balance, or what people also call them as mass balance. So actually, we're going to use this mass balance more when we talk about this materials balance. All right. So if we write an equation to describe this mass balance process, so what we can do is we can actually draw a control volume. So what a control volume means is a kind of a imaginary volume where you have the flow of the materials going in, going out, and you have the accumulation inside and also the consumption or creation inside, right? So this is an imaginary boundary that's describing the system with the materials balance or with the mass balance. So within this control volume, we can write out actually a mass balance equation, which is the purchased food, which is the input, right, is going to be equal to the consumption, the solid waste, and the stock. Okay, so let me draw a straight line here, and the stock. Okay, so if we further write it out in more simplified terms, what that means is the input is going to be equal to consumption plus output plus accumulation. Okay, so people also prefer to rearrange this equation so that you have the accumulation on the left-hand side. Okay, so I'll explain why we prefer to do that later on. So if we do it that way, then the accumulation is on the left-hand side of the equation. So that's going to be equal to the input minus output minus consumption. Okay, so further for simplicity, let's just write out the capitalized letters. Okay, ACCU, accumulation, equals to in minus out minus reaction. Okay, so here you can also see that I actually replace this consumption by the reaction. This is mainly because in the environmental engineering system, so for example, when we talk about the degradation of the organic fertilizer, right? So we gave this example in our last class. Let's say we have a farmland, which is dumping these organic fertilizer into a river, right? So what we know is that there are bacteria in the river that can oxidize these organic fertilizers and oxidize them into carbon dioxide and water. Okay, so basically these fertilizers are being consumed, right? That's consumption. So what that means is if we just choose a control volume that's set up like this, okay? So the input is going to be whatever amount that's dumped into the river for this section, right? So the output is going to be the amount of the fertilizer that's exiting this section, right? And also we need to consider the input from the upstream. Who knows, maybe there are some fertilizer already in the river, in the upstream, right? So these are the input. So we also have the output that's exiting from this section of the river, okay? And then what happens in the middle is that there can be accumulation. So what accumulation means is maybe these fertilizer will settle down onto the base of the river, right? So they can get accumulated at the basin of the river. And there is also consumption. So the consumption is basically the oxidation within the river by the fertilizers, right? So this is describing this, what is happening within this control volume. Okay, so because of that, we can also replace this consumption by reaction because the reaction is the only way to consume these fertilizers, right? So also, this works in a way that this equation writes out works in a way that reaction term is always positive, okay? So whenever there's consumption, the reaction term is positive. But let's just think about the creation. Let's say the oxidation actually creates carbon dioxide and water, right? So what about carbon dioxide? So if we're trying to build up a mass balance for carbon dioxide, then we know that it's actually not consumption. This is creation, right? So in that case, we need to replace this term, replace the sign before the reaction to positive term, right? Because this is creating the carbon dioxide. And actually carbon dioxide, the amount of carbon dioxide within the river is going to increase, and that's going to cause the accumulation on the left-hand side. Okay, so this is how we can determine the sign before the reaction. If it's being consumed, okay, for example, organics being oxidized, right, or some salt being settled down to the base, right, or let's say oxygen being consumed, then the term or the sign in front of the reaction should be negative because it's being reduced, right? But if it's being created, it's being there's a creation of these or production of these chemicals, then the sign should be positive. Okay, so this is how we determine the sign before the reaction term. And actually, for a lot of the wastewater treatment process, the sign here should be negative. Okay, because we're always talking about the removal or the consumption of these pollutants. Okay, so this is how we determine the sign. And this equation is actually very important. So let's just try to write out or try to understand its meaning again. Okay, so basically the accumulation is going to increase with the amount of input. Okay, so the amount of so what that means is this input is always going to increase with, or the accumulation is always going to increase with the input. The more input you bring into the control volume, the higher the accumulation. Okay, so we need to minus the output term because it's being taken out from the control volume, and that's going to reduce the accumulation of this mass of this material. Okay, and further we need to minus the reaction. So the reaction is also taking this amount of species from the control volume, and that's going to reduce the accumulation as well. Okay, so now we can give some examples of how to apply this equation. Okay, so just try to memorize this equation or try to understand it because it's very important in terms of the mass balance. Okay, so first let's think of a problem, or let's think of a system where there is no chemical reaction. Basically, there's no reaction or biological reaction, chemical or biological reactions. Basically, there's no degradation of the material. So a simple example for this system is basically for the wastewater treatment, actually the first step of a wastewater treatment plant. Okay, so the example is actually called a primary clarifier. Okay, so whenever you look at pictures of the wastewater treatment plant, you'll see these round shapes. And actually, these round shapes are cylinders. Okay, so you can see from the side that it has this vertical walls here, right? And also within this cylindrical shape here, actually we have the wastewater coming in and going out. Okay, although it's not shown directly at the top, but somewhere is actually hidden within this system, or maybe the outlet can be at the bottom, or the outlet can be the top, while the inlet is at the bottom. Okay, so basically we have this giant reservoir here where you have continuously inflow and outflow of the wastewater. But in the middle or within this process, you have the gravitational settling of these larger particles down to the base of this primary clarifier, what we call primary clarifier. Okay, so what happens is let's say if we draw a schematic diagram, this is a primary clarifier. Okay, we have this steel setup at the top, right? You have the wastewater going in and kinds of purified water coming out. Well, within this reservoir here, you have larger particles getting settled down to the basin or the bottom of this primary clarifier. Okay, so within this process, there is no chemical reaction, but there's accumulation of these larger particles, what we call suspended solids, or the SS. Okay, so then we can within this primary clarifier, we can build a control volume. Okay, so we have an inflow, basically an inflow of the SS, the suspended solids, we have an outflow of the SS, while we also have accumulation of the SS. Okay, so basically we can build up the mass balance equation where ACCU is equal to in minus out. Okay, there's no reaction term within this process. So basically, you can see that it's the same as this equation here. Okay, so we can use this mass balance to evaluate what is efficiency for the removal of these SS. So for example, let's look at this this set of conditions. Okay, so let's assume that the flow rate of the wastewater is 2 meters cubed per second. We have the influent SS to be 200 milligram per liter, and the effluent SS is 80. Okay, so the question is asking, what is the SS removal efficiency? Okay, so here, based on these two conditions, we know that actually the accumulation is just in minus out. Okay, which is equal to 120 milligram per liter. Okay, so what is called a removal efficiency? So within this wastewater treatment system or the primary clarifier, what we can say is that the solids, suspended solids, are being removed through this accumulation process. Okay, so the removed amount is just this accumulation amount. Okay, so the removal efficiency is just the accumulation divided by the inflow. Okay, so this is the eta term, or you can also write it as the concentration in minus concentration out divided by the concentration in. All right, so because of that, basically you can use this equation here, and by plugging in the concentrations, 200 minus 80 divided by 80, you get an efficiency of 60%. Okay, so this is how we can calculate the removal efficiency for a primary clarifier that uses mass balance, right? Because there's no chemical reactions. That's why the accumulation amount is just the inflow minus the outflow. Okay, so another interesting condition is you see here I also provided the flow rate of the wastewater, but is it dependent or is the efficiency dependent on the flow rate? Actually not, right? So the flow rate is basically going to control how fast these suspended solids are going to settle down. But finally, what it affects is just the effluent SS. Okay, so if you have a very flow or very low flow rate, then you have a longer time for these particles to settle down, right? I draw it here. You have a longer time for these particles to settle down or suspended solids to settle down. And that's going to reduce the concentration at the outlet. Okay, but if you have a very high or very large flow rate, then the time for the suspended solids to stay in the primary clarifier is going to be shorter, and that's going to increase the concentration of the SS at the outlet. But for this problem, it already provided you with the effluent SS concentration, so we don't need to worry about the this process or how the flow rate is going to affect the outflow concentration, simply because we already have this value here. So because of that, it's not dependent on the flow rate of the wastewater. Okay. So this is a simple example where we can use the mass balance to look at the removal efficiency of certain pollutants within the wastewater. Okay, so another example is actually more simple. It's more simplified in terms of this equation. So when we describe this system is under steady state condition, and there's no accumulation or reaction. Okay, so under steady state condition, what that means is actually there's no accumulation, because we know that if it's not under steady state, then there's always an increase of the, let's say, if we write out this equation, minus out minus reaction. Okay, so if it's not under steady state condition, then there's always an increase of the species within the system, right? So this is going to become a time-dependent system. But what steady state condition tells us that the species within the system, let's say dc dt, is always zero, okay? So the species, either the concentration or the mass within the system doesn't change with time. So what that means is the accumulation is going to be equal to zero. Otherwise, it's not going to be at their steady state. All right. So further, this condition describes that there's no reaction. So this will become a very simple system where it's just in equals out. Okay. So then you may wonder, well, this is too simple. Well, do we have any real examples of this? Actually, there are quite a lot in our daily life or in environmental engineering. So the most simple example is, let's say you have 2 cups of coffees, okay, right? So one contains less caffeine, the other contains more caffeine. Okay, so one looks like this. Let's say the other one is totally dark. Okay, so you realize that you cannot drink this one because this doesn't work at all. Well, you cannot drink this one either because it's going to keep you awake, let's say, for a week, right? So what you're going to do, you're going to mix them, right? So the mixing process is basically the process where in is equal to out, okay? So we don't have any accumulation of the caffeine within this mixed cup of the coffee, right? We don't have reaction that consumes or create caffeine. So everything is just the physical mixing, right? So the amount of caffeine into this mixed coffee and the amount of caffeine out of this coffee, right? So this is just going to be a physical mixing problem. Okay, so here I'm also going to give you a example, and we can also spend some time to discuss how we can solve it. Okay, so let's say that there's a storm sewer, okay, that's carrying snow melt. So especially during the winter, let's say in the Midwest, or let's say in Missouri, the snow, we see snow every year, but snow is actually not very frequent, right? At maximum, it might be 1 or 2 per week. So that's why we also use some salt to, let's say, spread on the road to just prevent some traffic issues, right? If it snows every day, then maybe it's not, the salt doesn't help anymore. So because we put the salt onto the road, then once the storm water, actually the snow melts, it's going to form a very concentrated salt solution or salt water. Okay, so that's why we have this sewer to divert this salt water into certain flow or into, let's say, a lake or a river, right? So that's going to be a physical mixing of this system. Okay. So for example, here, the storm sewer that's carrying the snow melt with a 1.2 gram per liter of salt discharge into a stream, right? Let's say into a river with 20 milligram per liter of salt. Okay, so if you just compare the concentration here, so one is 1.2, one is 20. Okay, it seems that the concentration of salt is much higher in the stream, but actually it's not. Okay, we need to always pay attention to the unit. So one is gram per liter and the other is milligram per liter. Okay, so milligram, 1 milligram is 1,000th of a gram. Okay, so if we further write this out, then this should be 1,200 milligram per liter. Okay, so generally in environmental engineering, we would prefer to use the unit of milligram per liter, or basically for mass, let's say for mass, we prefer to use the unit of milligram. For moles or for numbers, number of moles, we would use millimole. Okay, so for volume, we would use liter. So instead of meters cube or anything else. Okay, so in terms of time, It really depends. We don't have a specific requirement. You can use seconds, minute, or hour, depending on which process we talk about, right? So for very fast processes, let's say for the flow rate or the flow of the water, then we may use seconds. But for reactions, let's say a very slow oxidation reaction, it can be in days or months, okay? But for the other three units, we prefer to use milligram, millimole, and liter for these engineering calculations. Okay, so because of that, we also always need to pay attention to the unit conversion, right? Because we have 1.2 gram per liter, we need to convert it into 1200 milligram per liter of the salt, right? So then let's say, because this is a physical mixing process, then we need to draw, or we can draw a schematic diagram of this mixing process, right? So we have a stream that generally is a little bit wider, right? We'll also have a discharge of the salt water, which is generally at a lower flow rate. So under very rare conditions, we have a discharge that's much larger than the stream flow rate. Okay, so here I'm also giving you an example of this discharge system, right? So this pipe here might be coming out of the storm sewer that's built nearby a road, right? And then once the snow melt or the storm water is being collected, then they can get discharged into the stream that's hidden somewhere else. So if we draw out this schematic diagram, then this is what's going to be. So we have a salt water, or the storm sewer water, that contains 1200 milligram per liter of the salt. Okay, well, for the stream, we have 20 milligram per liter of the salt. So the flow rate of the snow melt is 2000 liter per minute. Okay, and for the stream flow, it's 2 meters cubed per second. Okay, so again, you need to notice that the units are different. So one is liter per minute, and the other is meter per second. Okay, so because of that, let's try to say that we convert everything into liter per second. Okay, so if it's liter per second, then we need to basically divide this 2000 by 60. Okay, so that's going to be liter per second, because each minute there are 60 seconds, right? And then for here, this is 2 meters cubed per second. So we need to convert it into liters per second into 2000 liter per second. Okay, so this is how we basically how we convert all the units into a same set of units before we try to solve this physical mixing process. All right, so the flow rate of the stream is going to be 2000 liter per second. Okay, well, for the salt water or the sewer water, that's going to be 2000 divided by 60 liter per second. Okay, so this problem wants us to calculate the salt concentration after the complete mixing. Okay, and further assess that, assume that the system is at steady state. So if it's at steady state, then we can use this equation here, where accumulation is equal to 0, right? And that's going to be in minus out, and there's no reaction of the salt. Okay, so basically what we have is in equals out. All right, so for mass balance of this problem, there are actually two mass balance problems. So one is the mass balance of water. Okay, so the second one is the mass balance of salt. Or I should say, this is the mass balance of the flow. Okay, so when you have two streams mixing together, the amount of the flow should be always the same. Okay, the flow rate should be balanced, right? So because of that, we can calculate that actually the Q mix is just going to be the two flow rates that's upstream of this system, right? So for this problem, we can choose the control volume. That's this, right? So you have the two inflows, right? And you have an outflow, okay? So the Q mix is just going to be 2000 plus 2000 divided by 60. Okay, so this is going to be the flow rate, right? And then the secondly is the mass balance of the salt, right? So we need to calculate what is the inflow of the salt species into this control volume. So we have two inflows. So the first one is coming from the stormwater. And what we need to do is just use the C, let's say we start to name it, right? So let's say this is the storm sewer. So let's just name it as CS, right? Storm sewer. And this flow is QSS, okay? Well, for the stream, let's say this is CS or CST, QST, okay? So basically we can set up the mass balance for the salt as CSS multiplied by QSS plus CST multiplied by QST. This should be equal to Q mix multiplied by C mix. Okay, so basically the inflow of all the salt should be equal to the outflow of the salt, right? So we have two inflows. One is coming from the storm sewer water, right, or the storm discharge. The other is the stream itself. That's upstream of this mixing point, right? So after mixing, we have this mass balance. We have this amount of the salt coming out, okay? So we can start to plug in all of these values, but here, let's say, actually we can try to plug in all of these here. So you can see that if you plug it in, that's going to be 1200 multiplied by 2000 divided by 60 plus 20 multiplied by 2000 should be equal to, we already looked at it, right? The Q mix is equal to this value here. So that's going to be 2000 plus 2000 divided by 60. Then you have the C mix, okay? So by plugging in all of these values, then basically here is a representation of the problem again, okay? So you have this physical mixing problem system, right? You can identify the control volume from the system, right? You have the inflow of the salt and also the inflow of the water, right? So based on the mass balance of the water, you have the Q mix equal to a QST, this is stream, or and also the QSE. So they name it as a sewer, right? So the QSE here, right? So basically, this is first the mass balance of the flow, and then based on the mass balance of the salt, then you can try to solve what is the concentration of the salt after mixing, right? So here, I'm just listing out all the parameters in, right? This is the equation again. And then by doing the calculation here, you can find that the final concentration is 39.3 milligram per liter, okay? So you can see that actually, by comparing the concentrations, right? So we know that for the stream, that's before the mixing is around 20, okay, 20 milligram per liter. And then the concentration for the sewer is actually 1200 milligram per liter, which is a very highly concentrated salt solution, right? But because we have a much higher flow rate of the stream water than the sewer water, so the concentration that has been increased is still not that significant, okay? So it just increased by around 19.3 milligram per liter, okay? So although in one way it might sound quite significant because it increased almost by 100%, but in terms of the absolute value, this concentration is much lower compared to the concentrated salt water that's within the sewer discharge, okay? So this is how we can use the mass balance to try to look at the physical mixing system, okay? So you can see that there are some commonalities for these two questions. One is the primary clarifier, where you just have the removal of these suspended solids, right? Where we had accumulation equal to in minus out, right? You don't have a reaction term. And then for this physical mixing, it's furthermore simplified. It's equal to 0, equal to in minus out. Okay, so the common feature for these two systems is that they don't have reaction. Okay, so what if there are reactions? Okay, so the reactions are going to make it a little bit more complicated, but we can still try to solve it or look at these systems one by one. Okay, so you can see the general equation we have for mass balance is the accumulation equal to in minus out, in minus out minus reaction. So when there's no reaction, we have the primary clarifier, right? When there's no reaction, no accumulation, we have the physical mixing, which is the storm sewer water, okay? But what if there are reactions, right? So we're going to have a little bit more complicated system. But by incorporating the reactions, what that means is we need to incorporate the reaction kinetics. So this goes back to the contents of our last class. We have the zeroth order, first order, second order reactions, right? Everything is related to the rate, reaction rate, which is minus Kc, right? Or just minus K or minus K squared, right? But as we said, the most common reaction we're going to deal with is the first order reaction. The rate is equal to minus Kc, okay? But not only it depends on the reaction kinetics, it also depends on which type of reactor it's using. Okay, it really depends on what kind of reaction we're trying to deal with, or what, and also what is the reactor we're using to let these reactions to occur. All right, so there are quite many types of reactors, but we're just going to deal with 3 types of reactors in this class. Okay, so we can have the batch reactor. Okay, so we can have the CSTR, or the continuously stirred tank reactor. Okay. And we can have the plug flow reactor. Okay, so for all of these reactors, we're going to use a first order reaction rate where K is equal to Kc, or K is equal to minus Kc. So first is the batch reactor. So in the textbook, it also has the name of CMBR. So it's, I think it's called continuously mixed batch reactor. Okay. Right. So what this means is that for this batch reactor, there's a basically a feed into the system at first, and then within the reactor, there's a mix and a reaction taking place. And after this reaction is being dumped out, it's being discharged. So here you can look at these diagrams for more direct understanding. So what happens is, let's imagine that we have a reactor or have a tank here. So first we'll feed in the influent, okay? So nothing happens within the reactor. And then we start to put in a stirrer within this reactor. Let's turn it on. So once it's turned on, there's reaction taking place, okay? So after a certain amount of time, then we're going to send all of these reactants to effluent, okay? So basically for this tank reactor, when it's being operated, there's no inflow or outflow, okay? So when it's being operated or when the reaction is taking place, there's no inflow or outflow. So let's think back on our mass balance equation again. Okay, so our mass balance dictates that um, we should have what? We should have accumulation equal to in minus out minus reaction. Okay, so when this batch reactor is being operated, then we know that in equals out equals 0, right? So accumulation is just going to be equal to minus of reaction. Okay, so what about the accumulation? Okay, so the accumulation is basically the change of the concentration for this species, right? So let's imagine that within this tank, there's a degradation of some organic pollutants. Okay, so we're trying to remove certain pollutants within the wastewater, right? So the change of the concentration is going to be dc dt, right? And since it's being removed, right, so the reaction term should be a positive term, right? So that's going to be minus kc. But this is actually the simplified version. But if we're talking about the more accurate version of this equation here, then the accumulation term should have a volume of the reactor in front. And also for the reaction term, you should also multiply the volume in front. So what this means is that accumulation, we're not talking about concentration here. We're talking about accumulation of the mass for these species, right? So the concentration multiplied by the tank volume is going to be the total amount or total mass of these pollutants, right? So the accumulation, strictly speaking, the accumulation term should be volume multiplied by the change of the concentration. And in terms of the reaction term, whenever we write R equal to minus Kc, this is just the reaction rate. Okay, but when we talk about the change of the mass within this reactor, we also need to multiply that by the volume of the reactor. Okay, so luckily, both of these terms get canceled, right? Then we can have dc dt equal to minus Kc. So here, what I want to point out again is that in this problem, the volume gets canceled, right? So you don't need to worry about the volume of the reactor. But there are systems, for example, the next reactor we're going to talk about, then we need to always write in this volume term to make sure that it is accurate. Okay. But here for a batch reactor, the volume can get canceled, right? So basically, we need to consider the volume in front of the change of the concentration, and also the volume in front of the reaction rate, right? So now we have this this differential equation. So dc dt equal to minus kc, right? So we know that basically the concentration is going to be the concentration multiplied by minus kt. So if you wonder how we get this solution here, you can go to the lecture for our last class, where we solve the change or basically the solution for a first order reaction. So this is how we can get the final solution here. All right. So our next reactor is going to be the CSTR. Okay, so the continuously stirred tank reactor. So let's discuss this reactor in our Wednesday's class. So I think that should be good enough for this class since we didn't have any time for taking the quiz, right? So you can see that the materials are actually quite condensed. So feel free to let me know if there are any questions. And again, I apologize that we couldn't meet in real time to discuss these problems. I know that if you have any questions, then you can also raise them during our Wednesday class or during our Wednesday's office hour. Okay, so that's all for this class, and see you on Wednesday.